we will be looking at number lines.
The number line dates back to around the 1800s via the Cantor. This is George Cantor.
Is the number line? Well, let's take a line over here. That should be good. Let's see. Can we turn it or anything? Yeah, good enough. So we have a line over here. Let's say we draw a 0 mark. Now there are things before 0, but we talk about that much later in our math lessons. So this is 1, and now let's equal space everything. So that should be 2, that should be 3, that should be 4, that should be 5, that should be 6, and we're going to do this all the way until 10. And 10. Now, so this is our number line over here, and on our number line we have 0, 1, 2, 3, all the way up to 10. Now, how can we illustrate a number line? How can we think of it? Well, in our first lesson about place value, let's remember what we thought about the candleberries and stuff. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, instead of drawing a full-on berry, I've decided to draw a circle. So 0 gets no circles. 1 circle. 2 circles. 3 circles. 4 circles. 5 circles. 6 circles. 7 circles. 8 circles. 9 circles. And 10 circles. And so now we see that it creates a little bit of a staircase. As we go from left to right, it gets bigger. And as we go from right to left, it gets smaller. Now, let's notice the same thing over here. So let's just erase everything we did over here, because we don't need it anymore. Also, we're redoing this 9. And so, now, this number line goes on and on and on forever. It doesn't just cover 0 to 10. It can cover all numbers. Does it stop at 1 billion? Say, no. Does it stop at 1 trillion? No. Does it stop at 1 trivigintillion? Or 1 Google? Or 1 Googleplex? No. There is no way that this will stop. Take the highest number you can think of, then add 1 to it. Boom. You've got a higher number. And don't say infinity, because, well, for our purposes in math, infinity's not a number. So, that means that there is no end. And plus, infinity is an arbitrary concept. So 0, 1, 2, 3, 4. So as we see, when we go from left to right, we get bigger. So 5, 6, 7, 8. But when we go from right to left, we get smaller. And so, now, let's give you a recap of decimals and stuff by using the number line. So now, on the number line, how would we graph a decimal? Well, we could graph a decimal by taking, say, let's say that we split this into tenths, which would perfectly fit with the number system we use. So let's see. Split that in half. 1, 2, 3, 4. And we're going to split this into fifths. That's accurate enough. And so now, let's say you ask somebody, what is this? Well, we remember that there are 10 slices in between. So if we split a circle to 10 pieces, not particularly good at splitting a circle to 10 pieces, but the fact is that I'm trying. So if we split a circle into 10 pieces, sort of like this, then each one of those pieces can be expressed as 1, which is the amount of parts we have, over 10, which is the whole. So I'm going to highlight stuff to make sure you know what I mean. So 1 is the part on its own. So let's decrease the thickness a bit. So 1 is this part as its own thing. And 10 is the whole entire circle. And let's just put this 1 over here again so you can see that. Alright. And so, this is what happens when we take a circle and split it into 10 parts. Same thing happens when we take an interval from 0 to 1. Split it in 10 parts. So imagine this whole thing, this whole circle is being, oh no, I didn't change the highlight. This whole circle as being one whole, 1. And so if you take all of the pieces of the circle, which would be 10, 1/10, then by adding everything, you would get 10 over 10. And what would 10 over 10 be? Well, that means that the amount of parts we have is 10. The whole thing. And so, that means that the amount of parts we have and the amount of parts there are is the same, which gives us 1. Because we know that since this whole thing takes up the entire circle is 1, that means this must be 1. And so, now, what is this say? Well, this is 1 over 10 as well. Because this is 1/10 of the pieces between 0 and 1. So, if you were to take this region, then it would have a length of 1/10. So this is 1 over 10. This is 2 over 10. This is 3 over 10. This is 4 over 10, and so on. In fact, you can sometimes even simplify your fractions. How? We'll take the case of 2 over 10. Let's re-illustrate our little circle diagram. So we take our circle, we split it. So I'm just going to draw this, and then boom. I'm a master at this. And so now we cut everything in half. And that gives us our 10 slices. And now, let's see what happens when we take 2 of the parts, like we said we would. Oh wait, we used red for the pieces. Now, when we take 2 out of 10, the critical thing to realize is that 2 out of 10, let's say you unite these two. That wasn't up to what was planned. Okay, good enough. We can just, oh goodness. Now I have to fix everything. But now, if we take our highlighter, put it again, and so now we've united this piece, and now the thing to realize is that if we took this big piece and laid it out 4 more times on this entire thing, so for example, over here, then over here as well, and then over here as well. Ugh, what the what's that? Then over here as well. And that, oh, okay. Something seriously weird is happening. Oh, what the? Something really weird is happening over here. Okay, so let's just say that if we took 4 more of these pieces, then we could cover the entire circle once again. And then the amount of those pieces would sum up to be 5. And so 2 out of 10 can also be represented as 1 out of 5. Because remember, you take the big piece and then you lay it out all over again, and that gives you 5 new pieces. And if you take just one of those big pieces, which is 2 out of 10, then it's just 1 big piece over 5 of the big pieces. I really wish I could show it to you, but the smartboard is just acting up at this time. So, we can simplify fractions like that, making this 1 over 5. So this is 1 over 5, this is 2 over 5. Because if we take 4 of those slices, small slices, that could make 2 big slices. 3 out of 10 is just 3 out of 10, which can't be simplified. So, now, this is the idea of fractions. But how would we write fractions more practically? Well, for that, we can use decimals. Fractions aren't really used when you're getting into later stages of math. Mostly, you really want to use decimals instead when you're working with numbers, later parts of math. And so, how would we represent, say, 1 over 10? Now, we already learned about place value. So, for example, this is the 10, this is the 1s. And I'm really hoping you watch that because I'm not going to go over it over here. But there is another part to the right, which is kind of like the opposite system we used with our number line, where we have the smaller things, the tens place, which we should not confuse with the tens place. They are not the same. And then this is hundreds, and so on. Now, tens, let's say we only have 1/10. If we only have 1/10, we write 1 in the tens place. If we have, say, 2/10 and 6/100, we write 2 in the tens place, 6 in the hundredths place. Speaking of hundredths, what is a hundredth? Well, it's 1 over 100. Then comes 1 over 1,000, 1 over 10,000, so on, so on, so on. Essentially, if you go this way, then the value of the digit is multiplied by 10. If you go this way, it's divided by 10. And so, now, that is the central idea of the number line. On the number line is basically an infinite little graph that can show you a list of all of the numbers. And so think of it as a list. And if you want to zoom in and look at smaller things like fractions, those fractions can be seen in between the whole numbers that are already on the graph. If you want to see subdivisions of those, then you can zoom in even further and further and further. What's shocking is that you won't really find a way to express the smallest number. In fact, there is no smallest number, just like there is no biggest number. You might think 0, but remember, there is something smaller than that. We'll get to later. And besides, what if you're talking about 1? If you have it, so let's say you have like a square. You have it. Then you quarter it. Then you have this again. Have this, have this, have this, have this. But no matter what, there will still always be a piece of the square. It's recursive. So there will never be any point where this pattern ends. And so there is no smallest number, just as there is no biggest number. There is a huge, infinite number line. And, oh wait, I forgot something. Let's say you have to deal with big numbers, like 1,000, for example. What could you do? Well, 2 methods. You're not going to stand there and chip off your pencil all day, writing all numbers from 1 to 1,000, are you? So you have 2 alternatives. Zoom out. That's what I like to call the first one. And destination. Which is what I like to call the second one. Obviously, the second one sounds cooler, but whatever. So zoom out basically tells you have to deal with all the numbers from 0 to 100. Just stop counting by ones. You can count by, say, 100 instead, can't you? And 1,000. And so, just zoom out. So you can't count by ones or tens or stuff like that. Just count by bigger numbers. And so, however, if you are asked to plot a point or a number that, well, isn't written over here, like for example 350, then you'll still have to be mindful. 350 is in the middle of 300 and 400. Or for example 325 is in the middle of 300 and 350. And so the destination method basically if you only need to deal with large numbers and numbers that are in their neighborhood. So for example, if you have 1,000, you could just put, I don't know, 995, 996, 997, 998, 999, then 1,000 over there, then 1,001, 1,002, 1,003, and so on. So you only need to deal with the numbers in its immediate neighborhood. You don't have to go all the way from 0. Just go to a number a bit close, to a bit less than this the thing you want to deal with, and then that's where you stop. You have your sort of destination where you get the number you're looking for and everything in its immediate neighborhood. So, for example, if you wanted 1,000 subtracted by 3, then instead of using the zoom out method, where 100 subtracted by 3 would probably be like here or something, probably like here. Instead, what you could do is you could use the destination thing. 1, 2, 3. And you would get to 997, something extremely precise. Is what a number line is. The third time I'm giving a finishing summary. And for real this time, this is a finishing summary. And the number line goes on forever and ever and ever and ever and never stops. And it can express whole numbers, but if you want to zoom in, it can express fractions as well. If you want to zoom out for the big numbers, you can use this. But if you only want to deal with numbers in big numbers and stuff in their immediate neighborhood, then you can use the destination method, which basically shows that big numbers and the numbers close to them. And fractions and decimals we learned today are also little parts of wholes that, when combined together, can make wholes, or whole numbers as they're called. And so this is the number line.